David. So I will be talking about lattice designs and their applications in plant breeding. So the outline of my presentation today, we'll start out with talking about incomplete block designs in general, distinguishing features in comparing one type of design with another, and then we'll talk about the lattice designs and basic plans that you can use and field layout. We'll do an overview of the statistical analysis. I'll present a lot of formulas. We're not going to go into detail, but there is an Excel spreadsheet available as a supplemental material, which you could use if you wanted to have more practice with doing those types of calculations. Then we'll get on to talking about the cyclic designs and alpha lattices, which are the type of lattice that I use most often in my own breeding work. I have a specific numerical example from my metafoam breeding program. I'll show you how I did the randomization and laid out the field plan, and I'll briefly present a SAS analysis with some interpretation. So I'll start by talking about blocking in general. We block experiments to reduce experimental error, to increase precision in comparing our different genotypes or treatments, and to make the conditions in which they're being compared more uniform. The problem that we have as breeders is that we deal with many treatments, many genotypes, and as blocks get larger, the condition within the blocks become more heterogeneous, making it more difficult to get precise comparisons between the treatments. There also may be other factors that limit the number of experimental units in a block. For example, if you're doing a growth chamber experiment, there may be a limited amount of space in there. In the greenhouse may be limited in space, or you may be limited in a field area you have available for your use. Also, if you're intending to do some kind of a chemical analysis, you may be limited in the number of samples that you can process at one time. So all these kind of situations would lead us to use some form of blocking. So incomplete block designs in general imply that plots are grouped into blocks that are not large enough to contain all the treatments. So there are some features that we use to distinguish the various types of designs, the number of blocking criteria, whether it's a one-way or two-way type of blocking, whether the design is balanced or partially balanced, whether or not it's resolvable, the shape of the design, and the process that's used for generating the design. And I'm going to be talking briefly about each one of these aspects. So in terms of a number of blocking criterion, if we're using an incomplete block design with a single blocking criterion, that would be analogous to a randomized block design. And so we have only one source of variation that we need to control. In some situations, use an incomplete block design that's based on a Latin square. In a Latin square, complete block design, you would have to have t-square observations, experimental units, to do the experiment, and that certainly may be impractical for large numbers of treatments. Another type of design with two blocking criteria would be a row-column design, and in that case, if it's an incomplete block design, either the rows or the columns could be incomplete blocks. Uden squares is another option. In that case, you would be taking a Latin square and simply dropping out two or more rows from the Latin square to create your incomplete blocks. So I want to distinguish between balanced incomplete blocks and partially balanced incomplete block designs. With the balanced incomplete block designs, each treatment occurs together in the same block with every other treatment an equal number of times. So I've shown here some notation that we'll be using throughout the webinar. T represents number of treatments. K is the number of units per block, so that would represent our block size. B is the total number of blocks in the experiment. R is the number of complete replicates of each treatment. And lambda is the number of times that treatments occur together in the same block. So lambda is related to the number of reps and block size and number of treatments in this manner. So with balanced incomplete block designs, all pairs of treatments are compared with the same level of precision because everything occurs the same number of times with every other treatment. So In the case of balanced incomplete block designs, we have this relationship that is required for balance. And you can see in this case that lambda has to be an integer. Things can only occur together 0 times or 1 times or 2 times. So it has to be an integer. And then we have these other constrictions here that the total number of plots has to be the product of the total number of blocks times the block size, which has to be equivalent to the number of complete replications times the number of treatments. So for example, if you have 10 treatments and with block size of 4, that would lead to the result that you'd have to have 6 replications. Lambda would be 2, so each pair of treatments would occur together twice throughout the experiment, giving you a total number of 60 experimental units. So in plant breeding, generally, the minimum number of replications that are required for balance is often too large to be practical. So we'll be talking about partially balanced incomplete block designs. In this case, different treatment pairs occur in the same blocks an unequal number of times, or some treatment pairs may never occur together in the same block. In this case, mean comparisons among the treatments have differing levels of precision. So certainly anything that any pair of treatments occurring in the same block are going to be compared with greater precision. This makes the statistical analysis more complex, but this is certainly the commonest situation for plant breeding trials because we have so many genotypes that we want to evaluate. When we talk about lattice designs, an important concept is whether or not it's resolvable, and the lattice designs are an important type of resolvable incomplete block design. When something's resolvable, that implies that the blocks are grouped so that each group of blocks constitutes one complete replication of the treatment. So you can think of, when I say blocks in the context of this webinar, I'm referring to the incomplete blocks, or you could even think of those as the subblocks. And replication generally refers to the grouping of all the blocks to form a complete replicate that includes all the treatments, sort of like a superblock. So the nice thing about resolvable designs is that the trials can be managed in the field on a rep-by-rep basis. So you can do your operations in stages. For example, you may not be able to plant everything on the same day. Weeding can be done in stages, and you have a way to control the variation that's caused by the differences in time. You can collect data on a rep basis, harvest, and so on. Another thing that could happen is if you have at least several reps, you could actually lose a replicate without losing the whole experiment. So, for example, if you had a mapping population in 3 different fields, you could lose one field, and the other 2 would still be perfectly good incomplete block design with 2 reps. Another thing that's really nice about the resolvable designs is that if you have 2 or more complete replications, you can analyze it as a randomized complete block design if it turns out that the sub-blocking, the incomplete blocks, are not effective. If there's no measurable variation among them, then you can just ignore them and treat the whole experiment like a randomized complete block design. So just to make sure that we're all understanding the layout here, for lattice designs, we're going to have complete replications. As shown here, we have 2 complete replications. And then within each rep, it's going to be divided into our blocks. In this case, we have 3 blocks in each rep. So our total number of treatments would be 15. We have 5 plots in each of our little blocks. K is the number of units per block, so our block size in this case, we have 5 plots in each of our incomplete blocks. We have 6 total blocks in the experiment, and we have 2 replicates of each treatment. And because it's resolvable, we have a new thing to define, and that's the number of blocks in each complete replication, S. In this case, we have 3 blocks in each replication. So there's various types of lattice designs. Square lattice designs implies that the number of treatments is a perfect square. And in that case, the number of blocks per replicate and the plots per block are going to be the same. And they're going to be the square root of the number of treatments. Now, for complete balance in a square lattice design, you have to have R equal to your block size plus 1, which makes a rather large experiment if you have very many treatments. Rectangular lattice designs are another option, and in that case, the number of treatments is equal to S times S minus 1, where that's how many blocks you have in each rep, and then K, the block size is also equal to S minus 1. So for example, if you have a 4x5 lattice, that would have 4 plots per block, 5 blocks per replicate, and a total of 20 treatments. With alpha lattices, we have more flexibility in our choice of S and K, and the only real constraint there is that the total number of treatments has to be equal to the number of blocks per rep and multiplied by the block size. So this is the basic plan for a square lattice. And as we said, for a balanced square lattice, we're going to have a number of reps is going to be 1 greater than the block size. So here we have 4 reps. It's a 3x3. We've got 3 blocks in each rep. And this is the way that you're typically going to see these plans in textbooks if you were to look them up. So this little square here represents a sub-block or an incomplete block. And those 1, 2, 3, that's representing the treatments that might occur in that block or the plots in the block. And so just to re-emphasize, by balance, we mean that each treatment occurs together in the same block with every other treatment an equal number of times. So in this case, if you look through this design, you'll find that, for example, entries 1 and 2 only occur together in that block 1 of rep 1. You won't find them together anywhere else, and any particular pair you look at will be occurring in 1 block in this experiment. So lambda equals 1. Many basic plans like this can be found in Cochrane and Cox as a good reference. So in terms of the randomization, once you have your basic plan, you want to have your blocks composed of plots that are as homogeneous as possible. So you choose your block arrangement in that way. You then need to randomize a basic plan. So you first would randomize the order of blocks within your replications, and then you would randomize the order of the treatments within each block. So for example, if you were doing a 3x3 balanced lattice with 9 treatments, you would come up with a random number sequence. Say for example, you have a rank of 2 here. That would imply that the first rep would go into the 2nd position, and then you would need to randomize the that's randomizing the order of the replications, and then you would need to randomize the blocks in reps, so you get another random number, and that would tell you that this first block here needs to go down into the 3rd position within that rep. So that would be your new plan. You would have randomized both the replications and the blocks within the reps. So some more definitions here. For partially balanced lattices, that implies we don't have a complete set of reps. So simple lattices mean that we have 2 replications. So to get a simple lattice randomization, you would use the first 2 from a basic plan. It probably wouldn't be worth your effort if you were dealing with a 3x3 or 4x4 because those are so small to begin with. 2 reps you wouldn't gain much by using the lattice in that case. Triple lattices have 3 replications, 3 complete blocks. So you would use the first 3 from the basic plan, and there are possible triple lattices for all squares from 3x3 to 13x13. And you can have multiple sets. You know, you could have 2 13x13, for example. But the analysis would be different in that case. Quadruple lattices have 4 replications, so you would use the first 4 from the basic plan. And some of these don't exist. There's no 6x6 and there's no 10x10, for example. All right, so I'm going to talk now a little bit more about the analysis. As I said, I'm going to present a lot of formulas. This is really just if you're particularly interested in knowing the ins and outs of the calculations and where all the sums of squares and so on come from. I also have an Excel spreadsheet that I've done all the calculations on, so you could look at that. I'm going to try just to walk you through sort of the overall strategy and not get too bogged down in the details. But we do need to understand what the model looks like. So if we have a single blocking factor, and that's what I'm going to be talking about today, is lattice designs with single blocking factor. You're going to have in your linear model, you'll have a treatment effect, a replicate effect, an effect for the blocks within replicates, and then your random error. So looking at the analysis of variance, it's going to take the same form regardless of whether you're talking about a simple, triple, or quadruple lattice. The first step you have to do is to compute two error terms. Error B is the variation, represents the variation among your incomplete blocks. And then the intra-block error represents the variation among plots within each block. So I also have here, as I said, I've provided formulas for those who are interested. They're pretty much standard, calculations for analysis of variance. The one difference being here that our sums of squares for blocks is adjusted. Basically, you're making an adjustment for how the treatments in that block performed throughout the experiment. So, and then we'll be calculating, initially we will calculate an unadjusted treatment sums of squares, and then as often is the case, we'll get our sums of squares for error by subtraction. So that would give us an initial analysis. So the first thing that we have to do is to look at the magnitude of the error among blocks and compare that with the intra-block error. If the error among blocks is smaller than the intra-block error, that means we really don't have any need to make any kind of adjustment for our treatments means based on the block effects. So in that case, we can just ignore our sub-blocking, our incomplete blocks, and analyze the experiment as if it were a randomized complete block design, just using those complete replications as our blocks. If we find that the variation among the incomplete blocks is greater than our intra-block error, then we're going to compute an adjustment, a weighting factor that we'll use to adjust our treatment means to account for the variation among blocks. So this is just showing how you could do that. So once you've established that there is a variation among your incomplete blocks, then you might want to test to see if there are significant differences among your adjusted treatment means. So you can then compute an adjusted mean square for treatments. To do that, you have to first calculate an unadjusted block sums of squares, but then ultimately you can perform a standard F-test for the adjusted treatment means using the intra-block error as your error term. And here I have formulas for standard errors. The important thing to keep in mind here is that the standard errors are going to be different depending on whether the particular treatments that you're comparing occurred in the same block or whether they were in different blocks. Obviously, if they occur in the same block, you're going to have a more precise comparison than if they are in different blocks. And then finally, you might want to calculate the relative efficiency to get some idea about what you gained in precision from including the lattice design, making adjustments for blocks. So to do that, basically you try to estimate what kind of error term you would have had if you had just analyzed it as a randomized complete block design, and that's what this formula, the first formula, shows you here. And then you just make a ratio if the error from a randomized complete block design is much larger than the error term that you were using for your lattice design. That means you benefited by reducing the error by using the lattice design. So any kind of relative efficiency that's over 100% means there was some benefit from the lattice design. And as I said, I have included a numerical example. This is showing over here ultimately the adjustments that you would make for each of the the blocks, each of the treatments that occur in those blocks. This is a 5x5 lattice with 2 reps, some barley data. I'm not going to spend a lot of time on this, but again, it's available for you if you want to work through the calculations. You can do this on a spreadsheet. And here's your second rep. So we have this representing an incomplete block here with 5 different treatments, and these would be the yields of the barley. So this is showing, as I said, you have to start out with your initial ANOVA, just comparing the magnitude of your block error versus your interblock error. And in this case, we do have greater variation among our blocks than we do within blocks. So we would go ahead and compute the adjustments, the weighting factors. And then this would show you, for example, how you would go ahead and adjust the mean for entry 1, for example. Without adjustment, the mean would be 15, and in this case, with the adjustment, we've adjusted it down to 14.69 to make it comparable with all of the other treatments in the experiment. Okay, and then the next step, as we said, would be once you decide you had a block effect, then you would go ahead and recalculate your adjusted treatment variation. So you could also then go ahead and do a F-test to see if you have significant differences among your adjusted treatment means. Okay. And then I have a calculation here showing how you would calculate the relative efficiency. In this case, you can see our estimated error for our randomized complete block design is larger than it is for the lattice design, which means we gained about 10% increase in efficiency from using the lattice design. Okay, now I'm going to talk about cyclic designs, and this is an alternative to using these extensive tables of design plans that I showed you previously. With the more formal plans based on balanced lattices, you have to be pretty careful about how you're assigning your treatments to your experimental units, that you don't make mistakes and mix things up during field operations. But these cyclic designs give you a little bit more flexibility. They're pretty easy to construct. You don't need large tables of plans. And basically, you start with an initial labels for your treatments, and then you simply increment. In this case, you were just incrementing in each incomplete block, incrementing each of the labels by 1. And then because we have 6 treatments in this example here, with the block size of 3, once you get up to 5, then you go back to 0. It's modulo 6 because we have 6 treatments. So this is just to show you that all you need in this case is an initial block. And then from there, a randomization is generated. And a good reference for this is Cool in 2000. But from the cyclic designs, another kind of breakthrough was in 1976 when Patterson and Williams came up with a way to construct cyclic designs that are resolvable. And so it has all the desirable features of the lattice designs because the subblocks do resolve into complete reps. So we find that alpha designs are available for many combinations that we just couldn't obtain from the older lattice designs. Similar notation, but really our only constraint now is that the total number of treatments has to be the product of the number of blocks per rep and the block size, the number of plots in each block. And so in this case, we have efficient designs that exist for some combinations for which conventional lattices don't exist. You can accommodate unequal block sizes in these designs. I find there's so many options of combinations that you can use. You can always put in a few more check entries. Particularly in large experiments, that's not a bad idea anyway. So I find I don't need unequal block sizes. I have enough options to choose from. 2 types that you'll hear about. There's the alpha 01 and the alpha 012. This refers back to the concept of lambda that I talked about. where lambda indicates the number of times that particular pairs of entries occur together. So you have, with the alpha 0, 1 is the most common. That means that a particular pair of entries will either occur together not at all in the same subblock, or they will occur together once. The 0, 1, 2 means you'd have what they call 3 associate classes. So some would never occur together, some would occur once, and then you'd have some that would occur in 2 different subblocks throughout your entire experiment. Okay, so if you wanted to, it's not too difficult to understand how the alpha designs are generated, but it's not really necessary to understand it either. There's some pretty good software out there that will come up with the designs for us. I like to use Gendex, and I've given the URL here for that. They actually have a number of modules for generating incomplete block designs. I use the alpha to develop alpha designs. And the nice thing about it too is they don't just give you a design, they select a design that's most efficient. And the recent versions of alpha can actually come up with designs for as many as 10,000 entries, which is very powerful. You can download an academic or evaluation copy for free, or if you want to buy a perpetual license, it's $299. So I would recommend this for anybody who's planning to be using a lot of alpha designs or other types of incomplete block designs. Cyclic Design N is another option. The Agrabase software has their own built-in system for generating the designs as well as for analyzing them. In R, you can generate these designs in R as well. I have used that as well for some of my oat trials. I have seen code for generating the designs in SAS as well, and I've given a link there where I found a good explanation of it. So for each of these different options in Lattice Designs, we can calculate something we call the efficiency factor. This isn't the sort of the after the fact efficiency that I mentioned earlier, where you're comparing the randomized complete block design to the lattice based on your actual data. This is sort of something you would do ahead of time to consider the upper bound in terms of what the efficiency of the experiment could be. So without going into a lot of detail, you can run these calculations. You want to make sure that you're choosing a design that has a reasonably good level of efficiency. In general, you find that larger block sizes are going to increase your efficiency, as long as you're not getting such a large block that they're becoming heterogeneous. So a good strategy is to figure out what block size you need based on your experimental material and your testing site and so on, and just establish a reasonable block size. So not to use a whole lot of small blocks, but basically rationalize and think how big a block you can really accommodate. Okay, so if you're going to analyze lattice experiments,